times pi to negative 2 times pi to positive 2 times pi. You better write this code down. I may let you to find the shape of a signal and upload the picture in the exam, okay? So this is the interval. Then I want to generate a wave. Let me generate a wave 0. This is just a simple wave sign on the time t. Okay? Now I want to plot this wave. It's a t and wave of 0. And I want to use the line as the type of the curve. Okay, this is the standard sine wave. Okay, now next step. Wave 1 equal to what? Wave 1 equal to 2 pi t. We have 2 pi t, 4 pi t, and 10 pi t. 2 pi t. This is wave 1. And we have wave 2 is 4 pi t. And we have wave 3 is 10 pi t. And I have an xt is add them together, right? You can wave 1 plus wave 2 plus wave 3 is xt. And this time I wanted to plot xt on the t interval, okay? This time is at t, and I still want to use the type of the curve is line is L, just L, okay? But I also want to add something at the title. I want to add a title. The title is like example complex wave, and I also need to add a straight vertical line in the middle of the curve, right? I use F line, A-B-L-I-N-E, and H is 0, and type is 3. I should have this is the plot. So we notice that this signal is the period is 1 and the amplitude is 2. Okay. Every 1 millisecond or minute something will repeat once, and the amplitude is 2. You can use R. I'm using R Studio. You can use MATLAB to generate this signal by yourself.
Can we check the code out one more time?
Huh?
Can we look at the code one more time?
Go what?
The code.
Okay. How to zoom? How to do the zoom? I cannot install the RStudio on this desktop, so I can only use R because there's an R on this. You can use MATLAB, you can use whatever you like to generate these figures. Okay. Okay. Why I give you this example? All right. How to represent the signals? We have option 1, we use a Taylor series. all the functions, all the signals can be expressed in this way. It's called a Taylor series, but Taylor series, how to say, is unable and not very physically meaningful. But these do have some applications. Okay, so we needed to find another way to represent the signal. That is our option 2. It's called the Fourier series and the Fourier transform. So who is the Fourier? Joseph Fourier in 1768 to 1830, and he had a crazy idea in 1807. Any periodic function can be rewritten as a weighted sum of sine and cosine of different frequencies. That is the idea of the Fourier series and the Fourier transform. So this is the any option 2. So any signal or any function can be rewritten in this way. Add the cosine and the sine together. Remember, it's a periodic function. Okay, periodic function. Okay, our target, for example, our target signal is this periodic square signal. How to use the Fourier idea to reach this goal? Add all the sine or cosine waves together. See, we have this one is we use the sine, okay? This is a sine wave, and this is another sine wave, but the frequency are different. Is higher frequency. If you add this lower frequency sine wave and this higher frequency sine wave, you can have this signal. It's kind of like this one, but not exactly. We need to keep adding the sine waves to this signal, okay? With the increasing frequency. You will notice the for the third sine waves, the frequency is higher than the second one. If we add this one to here, you will have this signal. And if you keep adding them until the infinity, you should have this signal, target signal. That is the idea of the Fourier series. Okay, you keep adding the sine waves with increasing frequency. And finally, you will get a signal very, very close to your target signal. That is the idea of the Fourier series. Before we go further, we need to do the math review again. It's complex number. We have the real number, right? 1, -5.2, and then pi. We have complex number. For the complex number, we have a real part, right? This is a real part, and this is the imaginary part. And what is I? I is the square root of -1. And in your double E major, and you use J instead of I. Okay, the same. For a real number, you can also express this real number in the complex number way. In the way of the complex number, the real part is -5.2. There is no imaginary part, so that is 0 in front of I. It's real number and complex number. Next. We have a new coordinate, is called polar coordinate. Okay, this is a complex number, a plus bi. We have the real part on the real axis. We have the b on the imaginary axis. Okay, what's this? The angle is what? If I use phi, the angle is what? The angle is a phase. What's this? Yeah, this is the amplitude. Great. So for a complex number, you can find the two information. One information is what? Is amplitude. Another information is the phase, is phi. Okay, phi is the arctangent of b over a, because b over a tangent phi is b over a, so the phi is arctangent b over a. Sorry, excuse me. Okay. For the complex number, we have two properties. One is the amplitude. Another one is called phase. For the cosine wave, we have three properties, right? Or sine wave. You have, let me see, omega t plus phi. You have the amplitude. You have the frequency information. You have the phase also, as well. How to do this? How to use the complex number to represent a cosine wave? Because cosine wave has one more property, is the frequency. So we can use the complex numbers to represent the cosine waves at varying frequency. For different frequency, for each frequency, we can use a complex number to represent the cosine wave at that frequency. So we use a complex number to represent the cosine waves at a varying frequency. This is the idea. Okay, so if we want to understand the frequency of our signal, we need to parameterize the signal by omega instead of x. For example, x is t, omega is f or something in your sine wave function, okay? So you want to convert this time domain or spatial domain signal using the Fourier transformation to frequency signal. That is our purpose. So this time we use the complex number trick. For the some determined frequency, we know this function can be write in the real part way plus the imaginary part way, right in the way of a complex number, and we have the amplitude, and we have the phase, and also we have the omega information. And if we have the signal in the frequency, we just want to call the inverse Fourier transformation is the IFT. You can get the your original signal. All the information are preserved. Okay, what is the periodical function? if there is a sum A for function fx such that fx equals to fx plus na, then function is periodical with period A. Okay, this is the example of the periodic function. And we have cosine waves. We have a cosine wave function. Then we want to have a larger 5 times amplitude cosine function. We times 5 in front of the cosine function. And what about if we want to move this cosine wave to left 3.14? So you add the 3.14, the whole series will move to left. If you want to move the right, you need a minus 3.14. Okay? What about I want to increase the frequency of the cosine function? You need a tensor number in front of x or in front of t. You can increase the frequency of the cosine function. So this is the cosine function, the form of the cosine function, right? A is amplitude, and K is the frequency, and the phi is the phase. And this is again is based on the Fourier analysis. Let me give you the example. This is a signal. We have a 2 pi ft plus the 1/3 of the sine 2 pi 3 times ft. Okay, so this is the mixture of the two signals. Before we go using the complex number and the formulas, let us get about the frequency. What is the frequency? We can decompose this mixture signal into two signals, right? One is the 2 pi sine 2 pi ft. Another one is 1/3 of a sine 2 pi 3 ft. And we have the first signal, the frequency is f, and the amplitude is 1. 1 and f. This is the first signal. The second signal, the amplitude is 1/3, and this time the frequency is 3f. So you converge the signals from the time domain to the frequency domain. This means you have two signals. One signal is f with the amplitude of 1. Another one is 3f with the amplitude of 1/3. So from time domain to the frequency domain. Okay. Again, for this periodical square signal, remember, if we want to reach this target signal, we need to keep adding the sine wave or cosine waves with increase the frequency to infinity. So we add once, what about add second, add third? We keep adding. Finally, we may have the periodical square signal. So your frequency spectrum will look in this way. The first one is f, and the second one is 2f, 3f. But the amplitude is decreasing because C is 1/k. Is amplitude is decreasing, but the frequency is increasing. For periodical square signal, the frequency spectrum should look in this way. Any question? This is from the first adding. We have frequency 1 plus the frequency 3. And we add again, add to infinity. We have this formula to represent a square signal, I mean a periodical square signal. And we have this frequency spectra to represent this periodical signal. Okay, so for the first one, the perfect sine wave, the frequency spectra looks in this way, just 2 bar, okay, because it's a fixed number. For the second one, it's a periodical square signal, and you will notice the frequency spectrum is in this way. It's quite similar like this, and with another part on the left. And for random signals, their frequency spectrum looks in this way. That is why we have the this spectral. This is the spectral frequency spectrum. We have this mixed this original signal. We need ×1 matrix to convert this signal from time domain to frequency domain. Okay. This is called a Fourier transform. We also can times a invert matrix in front of the frequency signal spectral, and you can get the original signal. This is called an invert Fourier transform. This is the image in the spatial domain. After the Fourier transform, you transform this image into the frequency domain. You will notice that this image is compressed. Okay, this is a large data sample, but this one is just compressed data sample. Okay. For our image, it is actually a function. It's a function what? You have x and y is a coordinate. At that point, I mean the point of x and y, you have another value is called intensity, is this value. Okay, to represent the color of the pixel. Okay. So we have the image with a function in this way. At different x and y, you have different intensity. You have the different intensity, and you represent this whole image. And you can using the Fourier transform to transform this number to the frequency domain. You also can do the inverse Fourier transform to restore this image from the frequency to the spatial domain. Give you some examples after that. So this is the continuous Fourier transformation. Fu equals to the, you do the integral from negative infinity to the infinity. Fx is the signal in the spatial domain or time domain. You times e to negative I 2 pi xu dx. And when you do the inverse, you want to, I think it's u, sorry, du. You want to convert the signal from a frequency back to the time domain or spatial domain. You just times e to positive I 2 pi xu. Okay. And what about if we have a finite Fourier transformation, we let xt, yt be a sample records of two stationary processes. T is between 0 to t. And we define the finite Fourier transformation is in this way. Okay, you have a, it's similar, but you do the integral from 0 to t this time, instead of negative infinity to the infinity. So for Fourier analysis, the first one, we have a high frequency signal, but the amplitude is smaller, right? We have the frequency maybe 15, but the amplitude is just 2. For the second one, we have a low frequency signal, but we have a larger amplitude. For this one, we have a mixture of the two signals. Actually, our ear performs the Fourier analysis. And I give you the link here. You can go back and play it. You can select a different frequency. Different frequency will give you different tones. And you can mix, and you can still tell the difference by your ear. So your ear performs the Fourier analysis. Transform the sound from frequency to sound. Okay, your ear actually performs the Fourier analysis. And iTunes also performs the Fourier analysis. You will notice there's a balance bar, right? In iTunes or some place. Actually, this one represents the original signal in different frequency domain. Okay. Again, we use the boxcar function. We have this signal. Is a periodic boxcar signal. Okay. And my question is, can this function be reproduced with cosine waves? Of course, yes. We have original cosine waves, and we add one cosine waves with a higher frequency. We have a new mixture cosine waves or new mixture signal, and we keep adding the increased frequency signal into this original one, and finally we can get the periodic boxcar signal. Now, I want to give you some examples about the high pass and low pass filters. One we use the high pass, one we use the low pass. Last week is just kind of principles, but this class gives you some examples. So what is the low frequency terms? So low frequency terms is close to the origin or is close to the edge. Low frequency is close to the original point. You still remember the frequency spectrum. This is F, 2F, 3F. So low frequency is close to the original point, and high frequency is close to the edge part, right? So we use the low-pass filter to do what? Low-pass filter is only the signals in the low frequency can pass. We use it for the blurry, make the image blurry. And we use a high-pass filter. High-pass only the signal close to the edge can pass to represent the high resolution part. We use the